Hello there. My name is Michael Tawonga Kamanga, chemistry teacher at St. Mary's Karonga Girls. I'm here to take you through chemistry from 1, and in today's lesson we are doing physical and chemical changes. So in physical and chemical changes, in the previous lessons we saw that a physical change is different from a chemical change. These changes are not the same. Can we remind ourselves what are the differences between physical and chemical changes? Can you recall some differences between physical and chemical changes? Indeed, a physical change is temporal, while a chemical change is permanent. In addition, physical changes, in a physical change, there is no formation of a new product. But in a chemical change, on the other hand, a chemical change leads to the formation of a new product. So, obviously, the two changes are not the same. They differ. They are not the same. So I'll take you through the chemical changes. So in today's class in particular, the success criteria of this chapter or lesson topic is by the end of this chapter, you should be able to determine the valency of elements and radicals. Determine the valency of elements and radicals. Well, chemical reactions are very fundamental processes in chemistry where substances known as reactants they undergo a transformation to form new substances called products. So the new substances they are produced as a result of reactants undergoing transformation. So they undergo a transformation to form new substances called products. Understanding chemical reactions is crucial for various scientific fields, including chemistry, biology, environmental science, and engineering. So the chemical reactions, without a chemical change, there is no chemical reaction. Without a chemical reaction, there is no chemical change. So as you can see, the chemical change leads to the production of a new product. Why? Because in a chemical change, the reactants undergo transformation. A chemical reaction involves the breaking of chemical bonds in reactant molecules and the formation of new bonds to produce products. This process results in a change in the chemical composition of the substances involved. Now, for chemical reactions and chemical changes, as I've already said, these two are closely related concepts in chemistry. And understanding their relationship helps in grasping how substances interact and transform. So a chemical reaction by definition is just a process in which substances, that is reactants, undergo transformation to form new substances known as products. So yes, for a chemical reaction to take place, there must be a transformation reactants should be transformed to form new substances known as products. And this transformation simply involves the breaking and forming of chemical bonds. So in a chemical reaction, there is bond breaking, then there's bond rearrangement, then there's bond formation. No wonder there is the production of a new substance known as a product. Now, these chemical reactions are characterized by changes in energy, color, temperature, and the formation of new substances with different properties. So a chemical change refers to a process where the chemical composition of a substance is altered. The chemical composition. This is a key, the two are keywords. Chemical composition. So in a chemical change, in a chemical reaction, there is change in chemical composition of a substance, resulting in the formation of entirely new products with different properties. So, what are we learning from this? It simply means that in a chemical reaction or in a chemical change, if reactants have undergone alteration, there is a formation of a new substance. And if you are to compare the properties of the reactants and products, they are not the same. A sign that there is indeed the formation of a new substance. So therefore, chemical changes are a direct result of chemical reactions. A direct result of chemical reactions. For example, rusting of iron. When there is rusting of iron, there is a chemical change. And when you are baking, the ingredients, they undergo chemical transformation. So there's a change in chemical composition of the ingredients to form a new product with different properties. Then there's valency or valence. So it is a fundamental concept in chemistry that describes the ability of an atom to bond with other atoms. So please take note of that. Therefore, it is essentially a measure of an atom's combining capacity, which depends on the number of electrons an atom can gain, lose, or share to achieve a stable electron configuration, often resembling the nearest noble gas configuration. So here we want to learn on how we write formulas, chemical formulas, because in a chemical reaction, remember, it is summarized using a chemical equation. So therefore, in a chemical equation, we use symbols of elements and we use formulas. So how do we write these formulas? We always use valency. Each element has its own valency. For instance, when we say water, this is a common name. Water, how can we write water? When we say this is the formula for water, how do we know that this is the formula of water? Or how do we come up with the formula of water? So we want to learn on how we write the chemical symbols of elements, compounds, molecules. So we use valency. Valency refers to the number of electrons an atom can donate, accept, or share during the formation of a chemical bond. The number of electrons an atom can donate, accept, or share during the formation of a chemical bond. That is valency. This valency is determined by electrons. So electrons, they're the ones which determine the valency. And which electrons are these? The outermost electrons, the valence electrons. Remember, the electrons are always found in rather in shells or energy levels. So we are concentrating on electrons which are found in the last shell of an atom or an element, because these electrons, they are loosely held to the nucleus. So valence is based on the number of electrons in the outermost shell, also known as the valence shell of an atom. So atoms typically strive to have a full valence shell, which for most elements means having 8 electrons. So if it has 8 electrons in the outermost shell, then it is full. This is known as the octet rule. Although we have few exceptions, such as the duplet rule for elements like helium and hydrogen. So helium and hydrogen, they follow the duplet rule. Types of valency. Valency can be positive, it can also be negative. So you have positive valency when atom loses electrons to form a positive ion. For example, we have sodium, it has a valency of +1 because it loses 1 electron to achieve a stable configuration. So this is positive valency. Then we can also have negative valency. The negative valency, when an atom gains electrons to form negative ion. For example, chlorine, it has a valency of -1 because it gains 1 electron to achieve a stable configuration. Okay, then we can also have neutral valency. Remember, we can have a positive valency, negative valency, and a neutral valency. So when atoms share electrons to form, let's say, a covalent bond, as seen in molecules like water, where hydrogen and oxygen share electrons to achieve stability. So if this happens, then there is a neutral valency. Now, allow me to take you through the valency of common elements. Valency of common elements. Hydrogen, which has a symbol H, it has a valency of 1, meaning it can form one bond by sharing 1 electron. Oxygen, it has a valency of 2, which simply means it needs to gain or share 2 electrons to complete its octet. Carbon, it has a valency of 4. It can form 4 bonds by sharing 4 electrons. So here we have the valency of hydrogen, the valency of oxygen, and the valency of carbon. Then, furthermore, nitrogen. Nitrogen has a valency of 3, which is typically, it forms 3 bonds or it can share 3 electrons. No wonder it has a valency of 3. So for these examples, now you can know that indeed valency is the combining power of an element. Number of electrons a particular element can gain, lose, or share. Gain, lose, or share. Now, the same valency is related to oxidation states. So valency is related to oxidation states, which indicate the degree of oxidation, that is the loss of electrons, of an atom in a compound. For example, in sodium chloride, sodium has an oxidation state of +1, reflecting its valency. So it has an oxidation state of +1, which by the end of the day is reflecting valency. So the valency can also be connected with the oxidation states. Okay, how can we determine the valency of a given element? So the valency can often be determined by the position of an element in the periodic table. For instance, elements in group 1 have a valency of +1. Elements in group 2 have a valency of +2, and so on. So the group number will always determine the valence as well. So the valency can often be determined by the positioning of an element in the periodic table. Briefly, we can also go through the valence of transition metals. Of course, in Form 1, this is not relevant. Can vary due to their ability to lose different number of electrons from their d orbitals. So that is just a brief description on the valency of transition metals. For example, if we go back to the valence of hydrogen, we said it has a valence of 1 because it can form one bond by sharing a single electron. Oxygen has a valence of 2 because it needs 2 additional electrons to complete its octet, allowing it to form 2 bonds. So if the valence is 2, the number of bonds is also 2. If the valence is 1, the number of bonds formed is also 1. Carbon, it has a valence of 4, which is why it can form 4 bonds as seen in organic compounds like methane. So therefore, valency is crucial for understanding how atoms interact and bond with each other to form molecules. It provides an insight into the chemical reactivity and bonding behavior of elements, making it a key concept in both inorganic and organic chemistry. So valency is very, very important. Let us go through the importance of this valency. The valency will always help us understand the concept of chemical bonding, that is formation of compounds, and even the bond types. Because how compounds are formed will always be determined by the valency. In other words, it helps to predict how atoms will combine to achieve stable electron configurations. The same valence will also explain the types of bonds formed, that is whether single, double, triple, and the bonding patterns in molecules. For instance, carbon's valence of 4 allows it to form 4 covalent bonds, leading to the structure of complex organic molecules. So valence helps us to understand chemical bonding in line with formation of compounds and bond types. Valence will also help us to predict chemical reactions, that is the reactivity and reaction products. So it will help us to give us the general overview on the reactivity. For example, the valence of hydrogen, as already alluded to, is 1. So it typically forms bonds with other elements by donating or sharing 1 electron. Then reaction products. Understanding valency allows chemists to predict the products of chemical reactions. For example, knowing that oxygen has a valence of 2 helps in predicting that it will combine with 2 hydrogen atoms to form water. It will combine 2 hydrogen atoms to form water. Valence will also help us to determine chemical formulas, whether empirical formulas or molecular formulas. So in empirical formulas, the valence aids in writing correct empirical formulas. For example, the valence of sodium and chlorine allows us to determine that their combination forms sodium chloride with a ratio of 1 to 1. That is the ratio of ions. Then there's also molecular formulas. The valence, it helps in determining the molecular formulas of compounds by indicating how many atoms of each element are present in a molecule. The same valence will also help us to explain bond strength and stability. In bond formation, I've already said that if the valence is 1, then it will form one bond. So it will help us to know bond formation and even the overall molecular structure. So the valence influences the geometry and structure of molecules. For example, the tetrahedral shape of methane is due to carbon's 4 valence bonds. The same valence also helps in applications in chemical reactions, that is balancing chemical reactions and even stoichiometry. Balancing reactions and stoichiometry. So this is because of valence. So it helps in calculating reactants and products in a reaction by relating the amount of substances involved based on their valence. The same valence helps in predicting physical and chemical properties. That is compound characteristics, coordination chemistry. All this is because of valence. In compound characteristics, the valence of elements affects the properties of compounds such as solubility, acidity, and basicity. In coordination compounds, valence helps in understand how central metal atoms bond with the ligands, affecting the structure and properties of these compounds. Then biological significance, that is for enzyme and protein function, and even nutrient transport. So all these can also be determined by valency. So valency plays a role in the functioning of enzymes and proteins, as these biological molecules depend on specific bonding interactions to perform their functions. Nutrient transport, the valence of elements like iron, affects their role in biological systems such as oxygen transport in hemoglobin as well. Okay, quickly, let me take you through the valences of the first 20 elements. Remember that I've said the positioning of an element in a group, that is in the periodic table, will also help you to know the valence of a given element. I said elements in group number 1, they have a valence of 1. So as you can see here, the first 20 elements, hydrogen, it has a valence of 1. Helium, it has a valence of 0. Why is 0? Why is the valence of helium 0? Good, because it is in it. It is already having a filled valence shell. So there is no need for it to form a bond. Lithium, valence of 1. Beryllium, 2. Boron, 3. carbon 4, nitrogen 3, oxygen 2, fluorine 1, neon 0, sodium 1, magnesium 2, aluminium 3, silicon 4, phosphorus 3, then sulfur 2, chlorine 1, argon 0, potassium 1, then calcium 2. However, I said valence can be positive or negative. So elements in the same group, for example, helium, lithium, okay, what else? Potassium, sodium. As you can see, they're having the same valence, 1, 1, 1. And this is positive valence. If you go to group number 7, you have fluorine, 1. What else? Chlorine, 1. So these are also having a valence of 1 because they have 7 electrons in the outer atmosphere. They'll need 1 for them to have octet. So their valence, as compared to the valence of group 1, their valence is negative. For group 1, it is positive. Please take note of that. So indeed, the idea of valence is very, very important. Then we also have radicals. We can also have the valence of radicals. You have hydroxide, it has a valence of 1. So the charge on that radical, the charge on the radical, the ion charge, is the valence. So for ions, for the radicals, we consider the charge on their charges. Their charge is the valence. As you can see, you have negative, that's why there's 1. Negative, there's 1. 1 here is silent. Where here 2 minus, that is why the valence is 2, because there's a 2 here, the superscript. 2 here, 2 as well. 3 here, 3 as well. So in summary, the valences of radicals, it is always given by the charge on the ion. The charge on the ion. Take note of that. Well, so we have looked at the chemical changes, the chemical reactions, and we have looked at the valences as one way of understanding, as an introduction on how we can write the chemical formulas. In the next class, we'll look at how now we can write the overall chemical formulas using the knowledge of valences. So in this lesson, I was just introducing the valences to you so that you should be conversant with the valences, because these valences will be used in the next lesson. So having gone through the valences, there is an activity here. This activity will help you evaluate yourself if you have really understood issues to do with valence. So it is one way of evaluating yourself. And please remember to give the feedback in the comment section. Provide your answers in the comment section, participate, and compare your answers with the suggested answers which you will be given. Remember, what you'll be given are suggested answers. So don't be limited to them. You can add more and more information. Our first question is, what is the valence of hydrogen and why? Then determine the valence of oxygen. Then what is the valence of sodium? And write the valence of chlorine and explain its significance. So these are the questions. Please attempt them, and all the best. Well, if you have further questions, you can always come back to us using this WhatsApp number, or help@xulendo.org, or visit Xulendo online or xulendo.org. We would love to hear from you. Your feedback is very, very important. For the resources, the references, I've used Excel and Succeed Junior Chemistry Book 1, Achievers in Chemistry Book 1, Jungle Chemistry Book 1, Samuel Kalia Chemistry Book 1. For illustrations, design, and graphics, these were done by Charlotte Browning and Dave Mumba on work Xulendo. For the photos, here are the links for the photos, so you can visit anytime you want. Well, until we meet again in the next class. Bye-bye.